Forget static illustrations in textbooks. The human heart is a relentless biological engine executing continuous, violent mechanical motion every second of a lifespan. This engine is highly compact. It is roughly the size of a closed fist, with 2/3 of its physical mass positioned slightly to the left of the body's midline. Structurally, it is a four-chambered muscular organ. Its strict mechanical directive is to sustain continuous unidirectional fluid circulation. To achieve this, the organ must solve a complex engineering paradox. It has to operate two entirely different circulatory loops at the exact same time. One loop drives oxygen-depleted blood to the lungs for gas exchange. The other forces oxygen-rich blood through the entire systemic body. The spatial constraints are extreme. It manages these divergent pressure systems within a tiny footprint, entirely avoiding structural failure or cross-contamination of fluids. Understanding cardiac anatomy requires deconstructing the organ into its functional components. It is a highly advanced, pressure-managed dual pump system engineered for survival. Any high-pressure mechanical pump requires a protective outer casing to operate safely within its surrounding environment. This 3D model shows that protective housing, known as the pericardial sac. It is lined with a specialized parietal serous membrane, allowing the organ to move without friction against surrounding tissues. Removing that sac reveals three foundational layers that form the actual heart wall. The outer layer is the epicardium, the middle is the myocardium, and the inner lining is the endocardium. The myocardium is the primary working layer. It is composed of thick muscle tissue responsible for generating all the contractile force required to push blood. Looking inside this coronal cross-section, the internal architecture divides into four distinct cavities. The two superior, or top, chambers are the right atrium and the left atrium. Their walls are relatively thin. Mechanically, atria act simply as low-pressure receiving chambers for incoming venous blood, requiring very little muscular force to operate. Below them sit the two inferior chambers, the right ventricle and the left ventricle. The ventricles require massively thick walls. They're the primary output pumps, responsible for forcefully ejecting blood out of the heart. Notice the structural asymmetry between the two. The wall of the left ventricle is significantly thicker than the right. In biological systems, form follows force. The left ventricle requires immense myocardial force to push blood through the entire body, while the right ventricle only needs enough pressure to reach the nearby lungs. Pumping fluid under massive pressure introduces a secondary mechanical hurdle. The fluid will naturally seek the path of least resistance, which often means flowing backward. To maintain a single direction of flow, the system relies on a series of high-tolerance failsafes. This schematic highlights the first tier of failsafes in blue, the atrioventricular, or AV valves. These are positioned precisely between the top receiving chambers and the bottom pumping chambers. On the right side sits the tricuspid valve. On the left is the bicuspid, commonly called the mitral valve. The second tier consists of the semilunar valves, highlighted here in yellow. They act as gatekeepers at the bases of the large vessels exiting the ventricles. The pulmonary semilunar valve guards the exit from the right ventricle, and the aortic semilunar valve guards the exit from the left. When ventricles contract, the intense internal pressure forcefully snaps the AV valves shut. This physically blocks blood from shooting back up into the atria. Conversely, as the ventricles relax, the exiting blood attempts to fall back into the heart. The semilunar valves catch this retreating fluid, instantly snapping shut under its weight. These alternating, pressure-driven mechanical closures ensure that chaotic muscular contractions result in organized, unidirectional forward propulsion. A common misconception is that a single volume of blood travels sequentially through all four chambers, from right to left in one continuous line. The physiological reality is entirely different. The heart operates as two separate parallel pumps that contract at the exact same millisecond. This animated cross-section maps the simultaneous flow. On the right side, the pulmonary circuit begins as the right atrium receives depleted, deoxygenated blood returning from systemic veins. The right ventricle then ejects this depleted blood directly to the lungs to receive a fresh supply of oxygen. At that exact same moment, the left atrium is receiving freshly oxygenated blood returning from the pulmonary veins. The left ventricle then utilizes its massive myocardial wall to pump this oxygen-rich blood out to the systemic circulation, feeding the entire body. This synchronized parallel routing allows a single organ to continuously balance the lungs' need for gas exchange with the body's demand for oxygen, keeping the two fluid supplies entirely separate. Sustaining this continuous pumping action creates massive, unrelenting metabolic demands on the myocardium itself. This presents a paradox. Despite housing the body's entire blood volume, the heart muscle cannot extract oxygen or nutrients from the gallons of fluid flowing directly inside its own chambers. To survive, the working tissue of the myocardium must be metabolically isolated. It requires a dedicated external power supply network. This exterior view illuminates that independent power grid, the coronary circulation system. The supply originates at the right and left coronary arteries. These branch directly off the ascending aorta to capture freshly oxygenated blood immediately after it leaves the left ventricle. These arteries embed deep into the muscular walls, feeding oxygen and nutrients directly to the contracting cells of the myocardium. Once the oxygen is spent, the post-capillary waste blood enters a system of cardiac or coronary veins for removal. Most of these cardiac veins drain into a large vessel called the coronary sinus, which dumps the depleted blood back into the right atrium to join the normal pulmonary loop. Without this tightly integrated vascular network, the hardest working muscle in the human body would starve to death while completely full of blood. Zooming out from these individual systems reveals a single, holistic machine. The structural foundation relies on thick layers of myocardium to provide the physical force required for circulation. The precision atrioventricular and semilunar valves provide the strict, reliable directional control necessary against immense, unrelenting internal fluid pressure. The internal architecture neatly divides into left and right chambers, managing systemic and pulmonary flows simultaneously without cross-contamination. And the external coronary network guarantees a constant supply of metabolic energy to keep the muscle firing. The capability of the heart rests entirely on the synchronized integration of these systems. Anatomical terminology, from the epicardium to the semilunar valves, describes precise structural adaptations. Each component is engineered to solve the complex fluid dynamics problem of keeping a human alive.